Hello, everybody. Oh, it's a bit loud, but should be fine. Okay, so I'm gonna have this talk about machine learning and TensorFlow and like a bunch of other amazing things. And you know, right now there's like much of hype about machine learning, right? There's people like I don't know, like yesterday I've seen like your tweets, and people were saying that we're moving from mobile first to like AI first, right? And Google, at last Google I/O were also saying the same, right? So everybody's kind of like shifting slowly focus from one to another. Can you see the slide, right? Yeah, okay. Otherwise I'm gonna be like very in the corner. And it's pretty cool like how many use cases around there. We started with some pretty simple cases when we were like really good at recognizing images and understanding like what is on the image, right? And if you watch the movie, who watched the movie Hitchhikers to the Galaxy? Yeah? Okay, perfect. There was this like amazing thing that called like a babblefish. So basically there's a cute, nice thing that you can put like in your ear and you can understand different languages, right? And you would say that sounds kind of like future, right? Super far away future. But turns out it's not, right? And for those of you who doesn't know that, it's a product that Google released or announced, wouldn't call it like released completely, some time ago. And they said that, okay, you're gonna have this Google Pixel bot. It's also a brilliant idea to call something Pixel if it's like you're trying to listen to that. Yeah, and you can basically translate the language in real time. So like you're listening to, I don't know, the Japanese, and you will get back translation in German. And it's basically very similar what Babelfish was about, right? And you would like things like, okay, but turns out, when we started with machine translation, there was like lots of statistics, right? There was lots of PhD people working on like every small piece of pipeline, right? How to do a like proper splitting to the words, right? How to see like what part of I don't know, of the language this word is, and it's gonna take like years and years basically to like understand those things and get those mappings. And now what we can do with increased capabilities of hardware, with increased data sets that we are having, we can just train it end to end. Means like we have a bunch of data, we have a bunch of resources, and somehow magically it works, right? And another example is from DeepMind. There was like a problem of generating voice based on text. And originally it was, okay, we know how the word sounds or like how every letter sounds, and we will try to concatenate the things together, right? Sounds like how people do that. Nah, not really, because it also depends like what you were saying before, right? What is your intonation, like what is, like sentence semantic, like how things are working. And turns out you can also like build some fancy, I don't know, deep learning network that will generate it for you. And this is like one of examples. But it also got like way faster. And again, it's like end to end. So pretty exciting as well. And if some of you have seen these pictures before, it's kind of like getting like yet another step that we are trying to use some reinforcement learning to also like train the systems. And eventually, like this, one of those examples is going to be using just image that we're receiving like from the same screen. Like nobody knows like, okay, what is the rules of the game? What we should be getting, like there's some reward feedback, but basically the system learns it like on its own. So it's pretty exciting. And obviously for those of you who know what exactly is happening there, it's not that, okay, now we like completely overcome humanity and like robots can do all this amazing stuff. Nah, it's like a bit of cheating, but it still looks pretty cool that they can win from like top players in the world. Yeah, who of you has seen this slide? Yeah, okay. So usually, like if you go to a conference when Google Earth is presenting any TensorFlow stuff, they're going to be like one of those slides, right? And ideas are that, okay, how we explaining how the things are working. We have like a bunch of layers, there's some connections, I don't know, we do some activations, bam, bam, and it just like works, right? There's like decisions that like cat and dog. Unfortunately, it's sometimes pretty hard to connect those points, right? And it reminds me how I was like always trying to learn how to draw things, and they're like, yeah, you want to draw an owl? Easy, right? Like one round, another round, bam, bam, it's already owl. Nah, it doesn't work quite like that. So I'm still not really good with those drawing things, but yeah. On the other hand, does it mean that we're gonna go like all this like hardcore and like really go like with all mathematics? And is there like only way to how to get to the field? Not really, right? It's like some people were saying that, you know, in order to drive like a car, right, you didn't really need to know like how your engine works, right? You can start at different level of abstraction. So you can see, okay, how my blocks are working, right? And after see like, okay, if I want to see deeper, like I want to go deeper, I can always like find this complexity. Yeah, so I'm not gonna go that deep basically in the slides, so don't be aware of that. Don't be afraid of that, sorry. Yes, and when I was giving this talk some time ago, I was saying something that, yeah, we will try to make it like super simple, everybody will understand it, and that's what people tweeted afterwards. No, I didn't mean that. Like, I do appreciate what people do in different domains, and the idea is not to say that data science, machine learning is super fancy, amazing, and you all will not get it. No, definitely not. I think it just depends on approach and like how you show in those things. Yeah, and another thing that I'm also going to mention here is that there are going to be like a bunch of lines of the code. Don't try to read all the lines and understand like every word that is written there. I'm going to share, like, if you see this format, it's actually a Jupyter notebook. Who knows what is Jupyter? Yes. So for those of you who doesn't know, Jupyter is basically, I don't know, it consists of two parts. Like one part is, I don't know, some kernel that does execution of your code, and another part is like a web server. So eventually you have something that runs in your browser and you can execute like every cell. So if I'm going to be showing you a code, that means that this code is like also going to be shareable like by GitHub, and you can also go through the same steps. So don't try to memorize this code and try to focus on bigger universe, right? Because the problem with universe and the same with like deep learning is that, you know, the field is like super wide, right? And as universe, it's also like expanding all the time. So if you will try to focus like on every small planet, right, you will be never able to go somewhere else. So try to just, you know, step back and see like a bigger picture out of there, and don't read all the code, please. I know everybody will still read it, but I'm just saying that. Yes. So I will start from kind of like setting up like a general problem set and like maybe showing a couple of pain points, because I think it's like, you know, like when I was preparing this talk, I was always saying like, okay, I'm having like way too much content and it's getting like super fast and stuff like that, but in many cases, like if you're showing like very small piece of the content, like you're really missing like all those connections like around, right? Why we do that? Like what is the problem? Like why we started to do all those things? And I decided that we're gonna go, you know, like a bit fast and showing different pieces, but it's still gonna give you like a bigger overview. Because, you know, if you wanna travel the universe, you're gonna go fast. It's a good excuse for speaking fast and showing lots of code. Yes. So we're starting with a simple problem, you know, something that can detect is it cat or not cat, because, you know, internet is built for cats and dogs and all things around that. So imagine in like super simplified case, we have this like cat here, right? We even don't do like any normalization, so we just receiving like every pixel like separately, right? So one can say that in super simplified example, right? You can just have some classifier that looks like this way, right? You're getting some input data. You can imagine there is some like, you know, magical weights that you use for that, and you have some biases, right? So eventually you just have, okay, those my weights that I'm having, those my input data. I do some magical nonlinear activation, and somehow it works. Yeah, it's kind of like doesn't really answer any questions, more like rising some of them. But I will explain like where is it coming from. So if you would go in terms of like some intuition, right? The idea behind also like how is it working, right? That like all those pixels that we are having somewhere here is going to be used for, you know, if like our universe is super ideal, like all cats have the same size, all pictures of cats all the same size, and most likely eye is going to be in the same position, right? Just to simplify it. Yeah, and eventually once we train the system will be able to understand that, okay, some of pixels should be like positively activated, means like there should be some eyes, and that definitely shouldn't be like, I don't know, like a long nose of like a dog, for instance. That's how it is eventually going to be working. Oops. Yes. If you're going to show like a couple of formulas, and there are going to be very few of them, like don't be afraid of that. Essentially, okay, we have this stuff with like some input data, we have some weights that we magically get from somewhere, we have some biases that also magically get from somewhere. And we're adding like also some non-linearity. And you would say like, yeah, but if you're saying that this stuff is going to be working anyway, right? Why would we need to have some non-linearity? Turns out that, you know, with having just like a linear like mapping of this like as output of the function, you cannot really increase complexity. So like if you will add like more layers, it will not actually work because you can just simplify this formula to the same one layer. So like all this linearity gonna stay like on the same. So it means that you cannot really you know, map like more complex functions. So we need to add something that it might be like a sigmoid, and you don't need to right now focus what sigmoid is. Just like keep in mind that we add something that maps like our input and output like in non-linear fashion, right? Okay, but if we have this model, how do we understand like are we correct or not correct, right? We need to somehow measure ourselves. That's when we start to define this like a loss function. An idea, like don't try to read formula, just idea for your intuition. And for those of you who know, like you will get it. For intuition, it's just more like, okay, if I'm getting like classification problem, like is it cat, not cat? How can I measure that my algorithm performing good or bad, right? And in this case, we're saying that, okay, we have some, I don't know, like result of our prediction and like what is like a real result, and trying to see how many of them are correct or not correct. And it's essentially goes like in direction of like a cost function that sums like over all of them. Yes, it is like a bit overwhelming, but we will like go away from those formulas, and you don't really need all of them to, in order to, you know, understand where it's coming from. Just like a small piece, you know, what we were talking in the beginning is like what they call inference, right? So like we got it magically, it kind of like works, and we want to like predict it. But in order to get it magically, we need to still like train it, right? And training usually takes some time, and you know, people call it like you know, backward propagation in a simple case, and that essentially means that okay, we have this imagination of the model, right? And we have okay, some input data here, right, in the beginning. We do some like amazing stuff with non-linearity, and after we got like output here. And backpropagation, how it sounds from the name of it, is basically trying to propagate back from, okay, from my results that I'm having back to the weights. And what we do like during this backpropagation, sorry, is basically trying to adjust with this like values of weight that we got like in the beginning. So we slowly, we have like a measurement to see like, okay, how much we are wrong about our understanding of cats. And after we're saying like, okay, is it helpful? Like, are we like super far away? Try to adjust it by a bit. I wouldn't go like super much into details. Just like for your intuition, we try to, you know, backpropagate and show it. In the code that I will share afterwards, it will have like more like step by step, and I can also explain like more in details afterwards. Yeah, so we're trying to propagate it. If we go in direction of, you know, like trying to implement it just like with some simple libraries like NumPy for numerical computation, it kind of stays the same way. So for, you know, trying to predict stuff, right, we still multiplying weights and our input data and stuff like that. And the backpropagation goes in direction like computing from the formulas that I had before. You don't need to like really go deep into that, and you can still get the slides afterwards. But the idea there that, clicking back, that based on this propagation, we can understand, okay, we got measurement to see how much we are off, right? Because in the beginning, we don't really know is it cats or not cats, so we get some, you know, almost random initialization. But with step by step, we can like slowly adjust and say, if I before was like super much off, right, I can be like slowly trying to do like radial descent, what they call like in literature. But the idea there is that you're like slowly optimizing your form, like your function basically based on your cost. So you know, it's like, okay, I was like super far away, I'm slowly like getting like adjusted and like closer to it. Yes, it is right now complicated, but it will get like simpler with like the next pages. Usually it gets like another way around. Yeah, so we have this like learning rate, we got some like update part, how to adjust it, and we do it like step by step basically. That's what we call like an optimization. And after in the model basically, right, one part would be just like trying to predict it. So like we're slowly trying to adjust and be like as close to what our original data was in there. Yeah, and as you see, like you like had some formulas that you don't really get like where they're coming from. You need to do some like optimizations that you don't really know where is it coming from. It's like many things, right? And if you have like a different models, you add like a different like type of layers, it's also getting even more complicated. Turns out that like some companies like Google and like other players in the market, they started to work on a framework that can, you know, it's like simplify things for you. So you don't need anymore, first of all, like focus on, you know, how to do like all this, how to backpropagate things, right? Or how to even like make it faster, because if you have like many images, you will have like quite lots of computation to compute. And essentially you would also need to like run it somewhere, like have some support of things. So on one layer, or like just like multiple layers, Google take care of making sure that it runs fast, that it knows like how to like backpropagate. So all this like complicated stuff that we spend some time like trying to understand what is that about, but basically it's getting sorted out for you. Plus they also do some like fancy matrix multiplication optimizations that run like way faster like on GPUs and like other things. So it's just like taking care of you. Yes, and after on top of it, maybe I'm staying like on cables or so, there's like a bunch of APIs that gives you access to low-level Python API, more like high-level layers API, and like Keras if you know that, and also like estimators and canned estimators that also like give it even simpler. So basically, the more you getting like up from those layers, the easier it gets. So like number of lines that you're getting like getting almost exponentially lower. So basically, canned estimator might build you a model just like in one line. So you don't need to know like how you backpropagate things. You don't need to know like what is your optimizer does and stuff like that. You're just saying like, okay, it's my input data, it's my output data, and just works from there. If you have seen scikit-learn, anybody has seen scikit-learn? Yeah, so there is like a simple interfaces for fit and predict and stuff like that. It just give you super simplified interfaces basically. Yes, so if you go like, I don't know, TensorFlow 101, and what are tensors basically, right? Imagine that we're defining like a constant, I don't know, 21 and 2, right? And we're trying to multiply it. So when we print like the first one, it's already going to be a constant, tensor, right? If you, oops, that was like many clicks at the same time. Sorry, let's go back. Spoiler alert, yes. Yeah, so you see result, now it's perfect. Result is also tensor, right? So basically, if you would imagine any kind of like graph, right, of multiplication, whatever you're doing, right, like every part of it, like every node of this graph is going to be also tensor. But what is interesting is that in this line, we just like trying to multiply two numbers, right? But nothing happened. Like, why is that? Because it turns out it's way more like optimized if you can, you know, store it like as a graph basically, and after lazy, try to like compile this graph to specific architecture. So essentially, what you do with TensorFlow, like till version 1.4, by default is basically you define like a session that might be running like on your GPU or like CPU or whatever else. And after you can say like session, please run me this graph. So this graph is eventually going to be having, if you print it like in a fancy way, it's going to be look like that, but in a proper way, it's going to look like that. So basically, we have like two of our constant, first and second, and it like connects to multiplication. So basically, it's a graph that we had. And when you run it, it will execute it. You can also just define the graph in itself, like in a session run, basically, and still get the same result. Oops, what was this wrong with this clicker? And what is also interesting, because, you know, okay, you have a graph, but if you just have like static values, it doesn't really help us that much. You can also feed the values inside. So basically, you can imagine this graph as a fancy function, and after this fancy function can receive some inputs, and you can execute those inputs like afterwards. Okay, sounds helpful. Doesn't really help that much with the original problem. So the problem that also people face, like once you write this graph, right, it's going to be executed like lazy some moment, like in the future. But turns out it's like super hard to debug it, right? Because no matter what you're doing, like no matter what dimensions, right? Because if you imagine multiple layers, right, your dimension should also fit, because like otherwise your matrices cannot be multiplied. And it's like super hard to debug those things. And if you comparing, I don't know, for instance, TensorFlow and PyTorch, like yet another like deep learning framework, people would be like, oh yeah, like with PyTorch it's easier to like debug those things because you can actually get it without like static graph, and you don't need to have a session for that. And just like less than a month ago, TensorFlow released a new version with eager executions that basically let you, like play around with that and get results like faster, and you can see like all these like small mistakes like in the beginning. It is not production ready, so basically you shouldn't be running like any production model is that, but if you want to play around, it gives you like more feeling of that. Yes. So you remember all those like formulas that not formulas, but basically codes that we were writing. Imagine that we've now been writing it like in TensorFlow, and it's basically like code of TensorFlow. You can basically skip the part with initializers because it's only like a way how you run it for like a proper use case. But what I want to show you in this case that, okay, like for every layer, you need to define those dimensions. You need to understand, okay, there's like number of input data that we are having, right? And like what should be like dimensions of like a next matrix, right? And if you look at this graph, like, or graph on this slide, first time you're like, yeah, but where is it coming from? Like, what is it like? How do we get those? If you spend a bit more time, you will get like, okay, for instance, like last one, yeah, gonna have this amount of like 6 neurons like in third layer, but it's still like hard to map those basically, and it's complicated. But on the other hand, it already gives like out of the box some like amazing things as, you remember this like a formula for cost function that we had in the beginning that like helpful for binary classification. Turns out you don't need to know it because it's already like predefined like a library function like in TensorFlow that already like implemented for you. So yeah, it's kind of easier, but still some problems are available there. So if we go like back to original example and trying to implement it, right? All of a cost function, if you skip 2 lines with placeholders, is basically, okay, cost is equal these functions, and after we can just run it with like our graph. Yeah, and forward propagation is basically pretty much similar what we had before, because essentially just like multiplying like different layers together and adding some non-linearity. In this case, it's like ReLU. Yes, and the model itself is basically the same. You have like forward propagation that we defined here. So it's basically weight to compute it. You have a cost that we defined before with all formulas inside. And you can even say, okay, now please like optimize it for me. There is already like a bunch of optimizers that have different behavioral. So you as a developer, you kind of like shifting your focus from, okay, how do I do derivatives, right? How do I try to understand what is the best for like a binary classification or like multi-class classification, like just toward directions like, okay, what function I should be running. So yes, getting easier. But we still have this problem with all these dimensions that we had there. So we need to solve it. Just as example, the models that we define, if we run it, we get something like that. So we have some number of epochs, means that we're going through the data set and we're trying to adjust like as close as possible. Like on this graph, you can see this cost function. There's like a small idea behind that we see like it's going down. That means that we're getting closer to the target values. So basically the model learns something there. And depending like on what optimizer you're using, it might be looking differently. Because for instance, with yeah, like with mini batches, it might be like more bumpy, but the general trend that if it's going down, it learns something because we're getting like closer in terms of like our mistakes that we're having there. Yes, and okay, we did some models, right? And it gets some information. Yeah, okay, this should be fine. But like, is it already done? Like, are we already can be like building like all amazing stuff? How long it takes? Turns out that companies were working on that with much bigger resources and like much bigger, I don't know, GPUs and money to spend on that. And they already give some, like giveaways to us. So for instance, there's like a data set that's called ImageNet that has like 14 million images, if I'm not wrong. And there's like tens of thousands different classes, right? And all big companies like Google, Microsoft, whoever else, they were like trying to build like as good model as possible, basically, in order to get some, good information. And they were like that nice, basically, that they decided, what if I share those things like with all those like nice people around, and maybe they're gonna use our cloud services. Okay, maybe it might be helpful, but you would say like, how is it helpful, right? Because they were training for their own problems, right? Turns out that while we training this problem, right, we can also get something valuable for that, because the network itself is not only like trying to understand that, okay, this is a cat, this is a chair, this is like a programmer, something like that. it's also meanwhile, while having all those like layers, it's trying to understand like some features of that. So it learns like a feature representations. So if you like remember like going from like left to right, from input to output, right? Essentially, your network will also learn some patterns. And like the closer to the left side is going to be the simpler ones, and the closer to the right side, they're going to be more advanced. So essentially, you're learning some representations, and those representations might be valuable for you. So once you're going to, like you can use like 95% of the model and basically having some feature representations like super high level and just train your model to understand that this set of features is most likely a cat. You don't need to like train it to understand that, okay, that's how most likely eye look like, that's how like tail looks like. You're just saying that if it has like eye and tail, like super simplified, it's most likely a cat, right? And that's basically what you're doing. You're like cutting off like a last layer that in many cases is going to be like softmax, and you're using this like dimensionality of whatever you have in like a base model, and you're trying to like teach there that this set of features belong to the class ABC. So you can reuse the things that were trained by bigger companies. Sounds helpful, right? Turns out that number of models that you're having is also pretty big, right? And not all of them are the same. So in the beginning, there was Lynette that Jan LeCun, the head of Facebook AI, was building like super long time ago. And there was also PGG16 that I cannot find right now, but yeah, it's here. And on this graph, you can see that, okay, on one axis, you can see the cost. So like how heavy the model if you put it somewhere, weight, and also how long it takes to compute that. On another axis, you can see like how accurate is the model. So basically how good feature representation you are seeing there. And it turns out that heavier or like the bigger is not always better. Because in this case, you can see that, okay, there is Inception V3 that is like relatively cheap, but it's also like pretty good. So it might be like a good hint to understand, okay, what models are good for, I don't know, maybe for mobile application when you don't want to like put that much of resources. And there's also a paper that you can read up and get like more details on that. Yes. And you were like, okay, but you were like talking about all this stuff and now those models, like how can we utilize them? And there's like many different ways. Like one of the ways you can download like a protobuffer file with all the stuff inside, and eventually you will be able to like import like, oops, my clicker is going crazy today and not going back anymore. Yes, you can get like a graph definition like from the like definition protobuf basically. Yeah, you can also like still visualize it and see like, okay, what is looking inside and do clicky stuff. But essentially, once you have, remember this like representation of the layers itself, it has also like a different like names of different layers. So you can say, okay, I would like to put my data of like image data into this layer, right? And get it, yeah, from the last layer that also has a name. Right now it looks like, okay, I don't know these names, but when you print it and you like go to the papers that describes the model, you can easily find this information. What it gives you back is basically, I don't know, like I think in this case it's like 2048 like digits basically, and those digits looks something like that. You would, okay, what is the point? Like how can I use it? Turns out that those digits also, because they represent some like high-level features, might be helpful to see like similarity, right? So in this case, if you, I don't know, would get like numbers of features and like put in some, I don't know, three-dimensional space, in this case it's a product called like a tensor board that's also part of TensorFlow, you will see that, okay, those images that look alike also have like a similar features, means similar digits in that. So distance between those two different vectors are like smaller. So it might be helpful if you're gonna build some, I don't know, image similarity, for instance, or you wanna take a picture of something and you'll find what is similar to that. Just a hint more of like from production use case, once you have like tons of images, right, you would like face a problems that now you need to compare all images with all images in order to find, like the most similar ones. Luckily for us, company like Spotify built a product called Annoy, super amazing name for a product. But the idea there is that they do like approximate index basically of those like neighborhoods. So like once you're adding that, they have like a fancy tree-based algorithm to understand that, okay, I don't know, this dot belongs to some like approximate neighborhood basically. And after you can easily like in super efficient way basically get, okay, I have this image with this like number of vectors or like features. please show me what is the closest to that. And yeah, this product helps you do that. So if you want to build it, you can basically just use it and yeah, use some inception model, use like a node on top of it, and it's even like hackathon doable. So basically you can build it in like a couple of hours. Yeah, but if it's still going back to like, you know, our TensorFlow, it was like still a bit of problems, right? It like looks a bit complicated, not so easy. And there is like a library that right now part of TensorFlow, before was like independent library. And that makes it like even easier. So if you remember all those like dimensions and like fancy way to do that, it's super simplified with Keras. So with Keras, it's like basically like English. You're saying that my model is sequential, means that every, I don't know, input from beginning like goes as output from one layer goes as input of another one. And after you're defining, okay, I need a convolution layer, just like a different type of the layer, and after you have activation and like blah, like other layers. And you see, it's like super easy to define those layers once you have some knowledge behind like what those are. And you remember, like we will define like, okay, how model looks like and like how to combine those things. Now you went like in direction of having like a simple line, right? We're saying that loss, so the way how we defining like how far we are from results that we're expecting, just like one line. Optimizer is also like one line, and after metrics that we would like to show is also like the same story. So you don't need to go back in the beginning and say like, okay, what exactly formula was this like for cross entropy, or how is it like called in I don't know, in TensorFlow? It's way easier. For fitting means like trying to train the stuff, like similar stuff. You're saying like, okay, this is my train data, this is my like labels. I would like to, I don't know, run it for 2 epochs and like some other things, but basically that's one liner to train the entire thing. You don't need to know that much there. You can always go deeper and understand like how exactly it does behind the scene, but if you would like to just start it, you can just do it like that. You can also eventually print that and show like, okay, show me a summary. Maybe I want to see how many parameters I use in every layer. So it's pretty transparent and visible. Not like my clicker. Yes, and you can also evaluate it. So you can see, okay, how I'm performing, right? Eventually, you will get some feeling and see like, okay, if my numbers of like tech score like is different from like validation score, what does it mean? But in the beginning, it's still like super helpful to just print it and see like, okay, what does it mean and like how I'm performing. Yeah, you can also save it. I was training something, I save it results somewhere. You can see like, okay, show me it afterwards, looks good. And you can load it, obviously, and you can again like combine the model to get it running afterwards. So you can get it, that somebody train it for you, you can load it and just show it. And it's also like, since we have like a hackathon day, in many cases when you have some amazing idea to do something with machine learning, first try to Google it. I bet there's somebody who already implemented it. Try to see if it's running, like what ideas there. Read the paper behind that, and only after start to implementing that, because most likely there's some knowledge behind that already. Yes, if you go like in direction of showing some example how to use those models with Keras, in this case we have like a mixed data set, means like we have handwritten digits. There's some like image preprocessing stuff to show like how image look like, and once we loaded the model, like on the slide before, we can just do like a model predict with information of the image data, and it will give you a result. So it doesn't look like much of rocket science for just like using a car without building an engine of the car. And you can do it even simpler, because like in the beginning I was showing like, okay, inception with there's some files that I got from nobody knows where. And turns out with Keras, you can just say like, okay, you have like preprocessing just for images stuff, and there's application with the model itself. So you don't need to even download it. Like Keras will do it like for you, and you can just get those results and like still like get a graph. And prediction part is pretty much similar. You have some like image stuff that like how you need to preprocess it, and in many cases it's also like a part of the library. But essentially, you just do like a model predict, and it's gonna show it how it works. So as example, we have this like another cat, and if you do like predict, you show like, okay, it's a lion with like label number, blah, and probability of like how sure the model that it's something like that. And what is also beauty about all this, like how deep learning is developing, is that in many cases it's kind of like a modular approach. So once we get something that can represent the features that we were like talking about, we can use for something more advanced. So one of examples like is image captioning. So if you would think about that, like 5-10 years ago, it's going to be like pretty complicated task. So ideas are that you have an image and you would like to have a system that will generate like a sentence to say what is in the image. Turns out that you can just start to combine those blocks together. So you already have things that we discussed like more actively about feature extraction, right? You can use some base models like inception with 3, for instance, that gives you this 248 numbers, right? Basically, that gives a representation. And after you can use like another part that called like recurrent neural network, basically, that has some understanding of those like words and their embeddings. And once you combine blocks together, you will start like, get some like a higher complexity of the task. And yes, it is like looks complicated from here, but once you look at the code, especially in Keras, it's just like adding like another 10 lines basically. In many cases, it's still like problem of having like a proper data set that like label for your cases. But in terms of like building those blocks, it's getting like easier and easier. Another good example is visual question answering. So the problem statement is basically you having some like a short videos, right? And you can be asking some questions like, okay, what the man is doing like on the whatever video, right? And essentially you will see like very similar like citizen of this universe. It's like one of them is we have this like image representation. In this case, we're using like a base model of VGG. So it's not Inception, it's just like a different model because author of this picture did it like in a different way. And after we have some part of, has some recurrent parts, that means that we not only take as like a snapshot, okay, image is basically like a snapshot of the state, right? But we also rely on, we have some connections, how words are like in the sentence are. And essentially it also like learns some representations of those sentences, right? And you can after combine not as a sequential model, but basically with 2 different branches and with a couple of, like another layers that call like a fully connected, you can see like a learned representation of that. Yes, it doesn't really, gives you right now, okay, I'm going home and I'm going to be implementing that, but it gives you, like a guidelines that, okay, that's possible, that's things that you can Google and you can take a look. And even for this part, you can easily find like things like on GitHub that will give you like a small data set with, like labels, and it will like train some things like on GPU quite fast. It wouldn't be like super ideal human accuracy video or question answering, but it still give you like a small ideas like that it's working. Like so basically getting it's like in a way of Pareto principle for a first whatever 60% goes like super fast, increasing like and improving like afterwards gets like super hard. But it's still like everybody can basically at home just have an account to like Google Cloud or other services basically train like one of the smallest like pretty fast. Yes. Since we already mentioned all those service providers, okay, we can't save a model, right? But how can I run it? Turns out that like TensorFlow has some special like server solution called like TensorFlow serving. So basically, essentially, it will load the models that you can iterate and like trying to find like a best parameter for that in the training stage. And after you just like use the same model to like serve them. So afterwards, you will have some, HTTP request with your image, and it will give you the most similar ones. And even if on this graph it looks complicated, it's still like doable like in like hackathon time frame, because like most of the models are just available and visible for you. Yeah, if you're gonna go like into deployment, there is like a different versions of Docker called like NVIDIA Docker that has all access to GPUs. If you want to run it like on premise basically, but you can also run it with different providers like as Cloud ML or some Amazon stuff, or you can also use some services that like more optimized for deep learning. Yeah, I wanted to say the name of that, but somehow I totally forgot the name. Like, just catch me afterwards. There's one that optimized for like using it with your Jupyter. So basically, it will spin up a session for you, and after you can in your browser just like click it and execute it. So it's pretty easy. Yeah, and you will like, okay, we have it for browser, but most likely at many DevFest, we have like a bunch of mobile developers as well. And what does it mean? Like, are we again like left it out and there is no easy solution? No, it's not like that. And even you know, for all those like Android things, they also have support of they also have support of TensorFlow. So some time ago they released like TensorFlow Mobile. So if you use a Gradle, like all you know, integration of this dependency is gonna take you just like one line, because those 3 lines you're already having, and you will get like dependency in your project. Essentially, it's very similar what we were using before. So you can say, okay, I have this like a model definition. I would like to put it somewhere like in assets of your like application, and after you can just define like inference interface. Inference means that you're going to be only getting like result of prediction. So right now it doesn't really make sense, and it's not supported basically to train on devices, but you can still like do prediction. There's also, if you're gonna run it, it's like similar way you're defining, okay, what part of the graph I'm using like as input part, and where I'm getting like result. In this case, it's pretty straightforward. There's also like a good Google Code Lab that basically show you how you can be running all this simple example with inception model, and you'll get result from there. It's actually code just from there, so you can easily go through that. You can clone from GitHub and get running. Lately, TensorFlow, they also released TensorFlow Lite. Right now it's still in like alpha beta mode, so it's not really production ready, but they also optimize it a bit, because in many cases, if you have, I don't know, 65 million of parameters, right, it might be pretty heavy to put in your application. It's not like super heavy, so you, I don't know, 3D game might be more heavy than that, but in many cases you can optimize it. So there's like a bunch of techniques how you can do some fancy way to reduce like how big values of digits we're using for storing that, and how we can you know, archive it like in a better way. And like a part of the story that what TensorFlow Lite does. In this case, your like a model file is going to be like a way smaller, and you can easily put it like on your file on your device. And it also supports like Android and iOS, if there's any iOS people in this room. Yes. So you know, it's kind of like pretty fast and many different like components inside. But as I said, idea was more like to give you like a bigger overview and give you understanding that it's not like 100% that you need to have like PhD in like applied mathematics or something. In many cases, you can be the one who can be, you know, like driving your car, not like inventing a new fancy way to inject fuel inside of your engine, because most likely we don't need that many people inventing the system. You can be just like writing that. And after, if you see that, okay, I really need to optimize like this part or another part, you can always from, you know, this like T-shaped part, go deeper and like go harder like on different things. So don't be afraid to try things, and just get it running like on your like some pet project, and get it from there. Because, you know, like we're switching from all this like mobile first to AI first, and it's amazing things to start playing around. So thank you. Yes, and if you have some questions, maybe I have some answer from that. Yes.
Thank you for this presentation. I have one question about the loss function and the optimizer. I'm a user of TensorFlow, but sometimes I'm confused about these two functions. There are a lot of built-in functions, and they could do something very similar. So can you mention some from your experience about this topic, how to choose a comfortable or suitable loss function that means the optimizer functions in my training loop later? Thanks.
So it's a very good question, because in many cases, you know, just like a building model has many different branches where you can go, right? Because you can select different like loss functions, you can select different like optimizers, and what many people do, and I do the same like on my side, is basically reading like lots of papers, right? Because lots of papers given like good examples what other people are using, saving lots of time from my side while trying to, you know, just going through different of them. Obviously, there is also like literature to say, okay, for binary classification, it's good to use this loss function. For like some other type of task, it's good to use something else. But unfortunately, there is no like a single like a mapping answer that I can like for any task like answer you right now. It's more like just read on like on papers that like people publish, because in many cases they're sharing also like a tiny tricks like what worked for them good, what is not. Because in many cases like number of hyperparameters, like that means that number of layers, for instance, right? Or how many neurons like in every layer, or how do we do like convolutions like from one layer to another, is something that right now we as like theoretically cannot really describe it completely, right? But we can still see like best practice and see like what is working pretty good. So for me, it's going to be like the easiest shortcut for that, to just see literature on the papers that like just published right now, like more or less on daily basis, and see what is working for different people. And you can see, okay, what is similar like problem domain, and see what people were using there. And in many cases, I'm really happy for machine learning communities that we didn't really have much of like paywall. So everything of that's like in open source. There is like a model that people also putting like online, and just going through those files helps you to have a feeling what is good, what is bad.
So it's just a common question to select a suitable loss function or optimized function. And we have to try with different functions to get a comfortable output. So we have to compare with different function. They are a little different in terms of the loss function, but the output can be more different if we choose different functions before. Sometimes I have the solution only to make more learning runs, and to make my loop more and more, and at last the result will be equally or similarly. But take more run, that means it costs more CPU time or GPU time. So it confused me so a lot of time about choice of loss function. Use TensorFlow, that means I don't have to have a professional mathematics background. So I'm looking for a better solution for my personal private applications. But it's really very difficult to final decision about these two kind of functions.
Yeah, unfortunately, like the domain itself is like relatively young, so like number of researchers like for that is like still happening quite actively. And as you said, that yes, we can compare it inside the same loss function because it's comparable data, but if you define it differently, we're just comparing like apple with bananas, but again, you can see how far you get with, I don't know, with actual results, right? Because you can see how, I don't know, like your precision recall, right? If you do like classification afterwards works, right? It is not like super ideal, yes, but it still gives you some hint like how far we end up like, after optimization of like as a baseline, right? I think we can discuss it like after the talk, because otherwise it gets like a bit deeper, like why is this loss functions are not comparable, right? Like what is it about? So definitely gonna talk with you like after this one. Anybody else? Yeah.
Just a short question. Thank you very much. Very great talk. I think short question regarding the TensorFlow and machine learning within your company. Do you do it? And if yes, which use cases do you have?
So this company that I'm working in, Stylight, this has like fashion e-commerce kind of domain. So we have like a bunch of images from like hundreds of different shops, means like different languages, like different locales. And we use it for extracting images, like pictures from images, to understand like what things are. To be honest, it didn't really, okay, now it's like skyrocketing, it's like way better, because as shops that providing those feeds, they also providing descriptions. So like if a shop providing like a good data in, we also getting like good classifications out. Unfortunately, not all shops providing like a very good description. So in many cases, it's also some crap inside, or description just like wrong basically. And in this case, we can find some like combinations of models that basically gets good features from one side and good features from another side. What people also in many cases kind of misunderstand that TensorFlow is not only for neural networks. Like in many cases, especially if you're using like a estimators API, it gives you like a very good, you know, transitioning from using like a simple model as, I don't know, like some trees, or like there is even like some kind of implementation of XGBoost like as a part of TensorFlow, and you can easily, you know, to switch from simpler model to something more advanced, right? Because if you use it like in old way, we use like XGBoost, and after we use like neural network, there's like so many different ways how I can like fail with that, because, you know, I do some like feature engineering, like, or pre-processing of data here, like in, I don't know, scikit-learn and in TensorFlow, and after something goes wrong because I didn't have enough sleep, and after I'm comparing like Apple and dogs basically, because I just like failed with data pre-processing. And while using the same interfaces on like feature engineering and pre-processing of this data, we can easily swap the parts in between. And right now they, you know, like extracting and like extend, like making like even more and more different like types of the model inside. So it's not only neural networks, so it's like still helpful to have it as like a baseline to easily swap those things. And with Starlight, I also answered like with images and other things. There's also some part with like that we're trying to do predictions and like other things, but I think the easiest and the most understandable part is like trying to extract like information from the images, and to image similarities that I mentioned. You can also like fine-tune it for like your own use cases, because similarity might be slightly different definition for different companies, and it's still like helpful. You can also do image deduplication. So for instance, like different shops providing different SKUs. They shouldn't be doing that, but sometimes they do that. And you can see like, okay, those are visually similar, or I don't know, you can find some complementary parts and stuff like that. So there's like a bunch of different use cases that we have like in our pockets. Yeah, if you happen to be in Munich, we have like a meetup about that. Just like swing by and ping me, like, I know, on Twitter, and happy to have you. Yes, let's call like that. Hacking machine learning, because hacking is a cool word. No kidding. We just go it like controversially, like in the way to like drop it and build it. Yes, and we have open positions. Like if you would like to build some machine learning pipelines with us. Thank you.